Imagine a radiologist. She reads an X-ray better than anyone on Earth. But show her an MRI? She's lost. Show her a blood panel? Useless. Give her a patient's spoken description of symptoms? She can't process the audio at all. For decades, this was the state of AI. We had one model architecture for text, a different one for images, another for speech, another for robot control. Each was brilliant in its lane, but completely blind outside it. A convolutional neural network could identify a dog in a photograph, but it had no concept that the word dog even existed. A language model could write a poem about a dog, but had never seen one. These weren't just different models. They existed in different mathematical universes, different coordinate systems, incompatible vector spaces. No bridge. This series tracks the end of that isolation. It is the story of how we moved from narrow specialists to the Omni model. One architecture, one training paradigm, shared representations, and capabilities that no one explicitly programmed.
Before 2017, every modality demanded a custom architecture. Text relied on recurrent neural networks, specifically LSTMs and GRUs. These processed input sequentially, token by token, left to right. They maintained a hidden state to carry information forward, but they suffered from a sequential bottleneck. To understand word 100, the model had to process words 1 through 99 first. Gradients vanished, long-range dependencies dissolved, and you couldn't parallelize training. Computer vision was different. It used convolutional neural networks. CNNs were fundamentally spatial. They swept small filters across images to build hierarchies, edges, then textures, then objects. Architectures like ResNet and VGG encoded a strong inductive bias called translation equivariance, assuming that a cat in the top left is the same as a cat in the bottom right. That works for pixels, but it makes zero sense for audio or text. Speech recognition was even messier, a pipeline of acoustic models, pronunciation dictionaries, and language models stitched together. Robotics used reinforcement learning in narrow, physics-based environments. The problem wasn't performance. These specialists were excellent. The problem was isolation. The vector for a dog in a CNN had no mathematical relationship to the token DOG in an LSTM. They were parallel universes, unable to speak.
June 2017. Vaswani and team publish Attention is All You Need. They introduced the transformer, centered on a mechanism called self-attention. Here is the mechanism. Every input token produces 3 vectors, a query, a key, and a value. Think of the query as, what am I looking for? The key as, what do I contain? And the value as, what information do I carry? For every single pair of tokens, we compute the dot product of the query and the key. A high dot product means relevance. We scale this by the square root of the dimension to stabilize gradients, apply a softmax to get attention weights, and use those weights to sum the value vectors. The formula is elegant. Attention of QKV equals softmax of Q times K transpose divided by root dk, all multiplied by V. But the real power is multi-head attention. The model runs 8 of these processes in parallel, letting different heads learn different relationships, syntax, semantics, position. The critical insight for Omni models is this. The transformer doesn't know what it's processing. It operates on sets of factors. It doesn't assume sequential order like an RNN or spatial locality like a CNN. Order is injected manually via positional encodings, sinusoidal functions that give each slot a unique signature. Because of this, the exact same architecture can process a sentence, a patch of pixels, an audio spectrogram, or a robot's joint angles. The paper's conclusion was prophetic. We plan to extend the transformer to input and output modalities other than text. They knew exactly what they had built.
3 years later, OpenAI asked, what happens if we make this architecture enormous? The answer was GPT-3. 175 billion parameters, 96 attention layers, a model dimension of 12,288, trained on 300 billion tokens, including Common Crawl and Wikipedia. The compute cost alone was roughly $4.6 million. But the result changed our understanding of learning. GPT-3 performed tasks it was never trained for. Zero shot, describe a task, and it does it. Few shot, show 3 examples, and it adapts. This is in-context learning. The model isn't updating its weights, it's learning from the pattern in your prompt. It's a form of meta-learning that emerged purely from scale. On aggregate benchmarks, it matched fine-tuned specialists in translation, arithmetic, and coding, all by simply predicting the next token. Crucially, performance followed a smooth power law. There was no ceiling, no point of diminishing returns. Bigger was reliably, predictably better, a relationship formalized in the Kaplan scaling laws. GPT-3 proved that a single architecture with a single objective on a single modality could yield general intelligence. The question became obvious. If text alone does this, what happens when we add vision?
January 2021, OpenAI releases Clip. The goal: teach a model that a photograph and a sentence are the same concept. The method: contrastive learning. Take a batch of n image text pairs. Encode the images with a vision transformer. Encode the text with a text transformer. Project both into a shared 512-dimensional space. You now have an n by n matrix of similarities. The goal is to maximize the values on the diagonal, the correct pairs, and minimize everything else. Clip did this for 400 million pairs scraped from the internet. The result was a revolution in zero-shot transfer. To classify an image, Clip doesn't need a specific classifier head. You just encode the image, then encode prompts like a photo of a dog or a photo of a car. You calculate the cosine similarity between the image vector and the text vectors. The highest score wins. It matched ResNet 50 performance on ImageNet without seeing a single label from the training set. More importantly, it was robust. On distribution-shifted benchmarks like ObjectNet or ImageNet Sketch, where standard supervised models collapsed, Clip held steady. It learned concepts, not dataset quirks. Clip proved that modalities don't need separate spaces. Text provides the semantic structure. Images provide the visual grounding. When they share a vector space, they create an understanding deeper than either possesses alone.
Clip was a retrieval model. It could match images to text, but it couldn't talk to you. DeepMind's Flamingo, published in 2022, solved this. The engineering challenge was delicate. You have a massive pre-trained language model and a massive pre-trained vision encoder. If you fine-tune them together, you risk catastrophic forgetting. The language model becomes stupid. Flamingo's solution was surgical. First, a perceiver resampler. It takes visual features of any resolution and compresses them into a fixed set of 64 visual tokens. This gives the language model a consistent interface. Second, gated cross-attention. They inserted new layers between the frozen language layers. These layers allow text to attend to vision. But here is the key. The gating parameter, tan alpha, is initialized to 0. At the start of training, the visual pathway is blocked. The model behaves exactly like the original text-only model. As training proceeds, the gates open, gradually letting visual information bleed in. Only 1.5 billion parameters were trainable. The billions of frozen parameters stayed intact. They trained on interleaved web documents, images and text flowing naturally together. The result? State-of-the-art on 16 benchmarks. 67.6% on VQAV2 with just 4 examples. Smooth scaling curves from 3 billion to 80 billion parameters. Flamingo showed us how to graft eyes onto a brain without breaking the mind.
Flamingo could see. Google's Palm E asked, "Can a model act?" They took Palm 540 billion parameters and plugged in a vision encoder and robot control. The architecture was conceptually simple but massive. Continuous sensor data, images, robot joint states, are tokenized and thrown into the same embedding space as words. The model processes the sequence, sensor data plus text, and outputs text that gets parsed into robot actions. You say, "Bring me the rice chips," and Palm E analyzes the visual scene, plans the motor functions, and outputs torque commands. It demonstrated multi-step reasoning and long horizon planning.
But the most significant finding was positive transfer. Training on robot manipulation tasks actually improved the model's ability to answer visual questions. Training on visual QA improved its ability to control robots. Physics made the language better. Language made the robot smarter. At 562 billion parameters, Palm-E was the largest vision language model ever built, proving that at sufficient scale, skills bleed across modality boundaries. Every modality makes every other modality stronger.
While Palm-E was a giant, DeepMind's Gato was a generalist. Published in 2022, Gato was small, only 1.2 billion parameters, but it was trained on 604 distinct tasks, 57 Atari games, image captioning, chat, robot arm manipulation. The secret was universal tokenization. Everything becomes a token. Text, sentence piece. Images, 16 by 16 patches projected into embeddings. Robot joint angles, discretized into 1024 bins using mu-law encoding. Discrete game actions, just integer IDs. All of these flow into a single standard decoder-only transformer. No specific heads, no routing. The same weights that process a pixel in Breakout process a verb in a sentence. The results were staggering. On 450 out of 604 tasks, Gato matched or beat specialist agents designed for those specific jobs. It could switch context instantly, describe an image, then play a video game, then stack blocks with a real robot arm. The scaling curves parallel language models, make the generalist bigger, and it gets better at everything simultaneously. Gato was the proof of concept for the Omni thesis, not the biggest model, not the best at any one thing, but one model, one architecture, doing absolutely everything.
When we look at the arc from 2017 to 2023, we see three independent threads colliding. First, architecture convergence. The Transformer 1. The same self-attention block now powers GPT-4, vision transformers, and robotic controllers. We no longer need modality-specific designs. Second, scale convergence. We found that power laws are universal. Whether it's text, pixels, or actions, performance improves predictably with compute. There is no ceiling, only a budget. Third, representation convergence. Clip, Flamingo, and Palm-E proved that disparate data types can share a single mathematical home. Text, images, and physics can live in the same vector space. When you combine these, one architecture, infinite scale, and shared representation, you get the Omni model, a system where cross-modal reasoning isn't programmed, it emerges.
We are barely at the starting line. The roadmap for the next generation is clear. Video understanding is next, processing hours of temporal context, not just static frames. Embodied agents are maturing, closing the loop between digital thought and physical action. Compositional reasoning is emerging, models that don't just see a physics diagram, but derive the equations and solve them. And tool use, agents that write their own code and call APIs as a natural part of thinking. In the next 3 episodes, we will dismantle this machine. Episode 1, How does the world become tokens? Episode 2, Why does scale beat specialization? And Episode 3, Are these models actually general? Omni models are not specialized. They are trained to absorb modalities. And what emerges from that absorption is something we are only just beginning to understand.